Beautiful camera. Anyway, so yeah, like I said, I'm Andrew, and I'm gonna, well, yeah. So Zach has written down that I'm gonna talk about Bionics, which, as he has briefly described, is the interface between like humans and machines, which is kind of like rather actually what you said was, I think, to maybe misquote you, was something along the lines of using machines to advance human capabilities. I gave myself the title Mirrored Bionics because actually what I'm more interested in is kind of the exact opposite. Like,
cool.
And I'm just gonna like go a little bit off track here. Like, I don't have as structured a presentation as I would like, because I've spent the last week or so just getting diving into the world of programming, which is tons of fun. And basically, I'm a biologist who digs on technology, and so that's where the whole programming thing comes in. But lately, or rather, since finishing my honours thesis, I'm actually really interested in this field called neuromorphic engineering, which basically is doing just that. It's taking the design of this, well, in taken literally, it's taking a central nervous system and reverse engineering it, basically. So to start with, I want to start with a fairly common, and talking about a fairly common technology, right, that you're all fairly well familiar with, and talk a little bit about a couple of ways that an understanding of the central nervous system has helped us to improve this particular technology, and then like later on, I'll get to touching on to what we can do with other technology, but first we'll just stick with cameras and see how this goes. But like, I mean, for those of you, like, I mean, everyone knows what this thing is, but I mean, I don't know how many of you know how, like, at the end of the day, how this thing works. I mean, you take some light, you've got a sensor at the back, and you, in principle, what you're doing is you're integrating. Let's not use a complicated word. What you're doing is you're adding up all. Let's just take the exact synonym. So you're adding up all the photons that hit this detector within a certain period of time, and you're using that to construct an image. Like, I mean, this is an example of a film camera because I'm a bit of a hipster, but like in practice, the cameras that you're probably more familiar with have like a CCD detector or CMOS more likely, which basically is just an array of diodes, that when a photon hits it, it produces some sort of charge, right? And so it keeps building up, and then when it hits a certain charge, it says, okay, I've captured X many photons, my output is 256, or maybe 256, but whatever. So yeah, that's cool. Like, there's a couple of ways, there's a couple of things that you can do to this particular technology to improve its performance in low light conditions. Because this works fantastically when there's plenty of light around, because, I mean, that's what you're doing, you're capturing a lot of light. But when we're talking about situations where there isn't so much light, like in the dark, like, I don't know if any of you have actually tried this, like taking photos at night time can be a bit tricky, and you've got to trade off between three things. You've got the sensitivity of the sensor that you use. Most people won't play with ISO unless you're really a photography junkie. And basically the ISO determines how sensitive that detector is. The more sensitive it is, the more noise you introduce into the system, because it can end up just responding randomly. The other two that you're probably more likely to play with are the exposure time and the aperture, which is hardware element of the camera itself. That's how large, basically the depth of field, and so how much light can get into the body of the camera. So, like, exposure time is could be thought of as, in this case, it could be thought of as a hardware thing, but in like a digital scenario, it's actually more a software thing. Same with sensitivity, that's a software thing. The aperture itself, that's hardware. Like, and when we're talking about biological things, there aren't that many modifications that you can do. Well, modifying hardware takes a long time, right? So can we go to the next slide, please? So anyway, this that you can't really see very well is a compound eye, and an example of not being able to modify the hardware. Like the eyes that you're familiar with in that particular camera, like that's got you can change the aperture to whatever you want, right? You can open it up or close it down. When you're talking about something like this, like this is a fly, but what I really want to be talking about are these, but forget about that. It's got compound eyes, right? It can't modify the depth of field of each of those lenses. It's like these. So the fly that, or rather the bee that I want to talk about for a little bit is this cute guy. His name is Micallef, right? And he or she, it's probably a she, it's a bee. But so they live in the rainforests in Madagascar, and they fly around. They're nocturnal, right? Which, for something using a compound eye, is again really cool because compound eyes are really bad at absorbing light. Okay, your standard design of compound eye. We'll see it on the next slide. But don't go. Well, maybe go forward. Just shoot forward. So the standard design for a compound eye looks something like this, and this is a kind of complex slide. But really, all I care about is this part of the slide. And maybe that's where it actually gives you a description of the photodetector. But essentially, you've got an array of cameras all set up pointing in different directions, right? And when we're talking, you know, light will come in, right? And depending on the angle at which the light comes in, it will be able to travel in a straight line down to one of these detectors. Well, actually, this whole body here is the detector. You can see it in the schematic. Like, section view, like this whole thing is one big detector, and so any light that comes in at an angle such that the lens can focus it down will trigger this particular photoreceptor. But the thing to know with compound eye is this green, the stuff that they've drawn in green here, right? This is like pigment, and so any light that kind of comes in on an angle, right? If it hasn't hit any of the other detectors, it won't, because light is discrete elements, right? Don't even know why. Anyway, the point is, like, the light will come along and it'll hit one of these, and if it isn't at the correct angle to be focused down here, it's just wasted, you know? And so you end up having a situation where, like, for night vision, this is not what you want to be doing, especially, like, you don't want to be wasting the light, because there isn't that much available, especially when we start talking about the rainforest, which it turns out, I really would like to give you like a cool sense of just how much light there is in a rainforest at night time. It's measured in thousands or millions of candles, which I don't actually know what that translates to. I do know it's a very small number, and when we start talking about numbers of photons hitting the lens of the camera, that's probably in the order of like a couple of hundred an hour or something, but I can't give you like it's probably like it's dark, okay? What's wrong with that? But yeah, so anyway, so Micallef that we saw on the previous slide is still able to fly around at night. And part of that comes from the way that its eye is designed to shoot forward, actually. Shoot forward. So that's an example of the nighttime photography, like one of the ways that you can compensate to open up the shutter speed, like I will slow down the shutter speed, and then you use detail, like you can't see any of the cars in the previous slide because there was cars. Not an issue in the rainforest. So that's kind of the standard design for the composite eye, compound eye. Whereas this is the design that nocturnal insects have, where rather than these ridges here, these pigment cells, they basically get drawn all the way up here. And so what ends up happening is here you've got a situation where you've got one lens per detector, whereas this one we've got multiple lenses all focusing to the same point. And so any light that's in this massive area is going to be transmitted on this detector. And so this is essentially what we're doing, is downsampling from space. So we're taking a fairly, like, I mean, it's already crap resolution. We're taking something that is already crap resolution and just reducing it like by a factor of 4 or something already. And then like that, there's a limit to how far you can do that before the amount of fusion you get is actually useful. because that's what we're talking about. We're talking about an animal that can fly. And so what this particular insect does is it actually has a kind of software solution to this problem which complements the design of its eye. In that, I really would like to have like a video to show you because no, there isn't one on the next slide. I really would like it though, but it turns out that this particular algorithm is a proprietary algorithm, and so like I took a snippet of one of the frames, which is step forward, and this is a snippet from the textbook, but the actual algorithm that this video that this algorithm is being shown here is owned by Toyota, and they're really keen on it. And so anyway, point is, what the dudes, this is a group run by a guy named Eric Warren over at the University of London in Sweden, and what they did was basically reverse engineer the algorithm that this eye system, the eye that the is using, and actually what's happening in this. So this is the raw footage. They take some raw footage, right? They've just ramped up the contrast here, and then they've applied a smoothing algorithm. And what's cool is the smoothing algorithm, because what it's doing in this particular example is this isn't just like a simple blur or anything. What they've done is they've basically created. So you know how any video footage that you get is actually, it's three-dimensional, right? You've got the X and Y coordinates of any particular pixel, but then you've also got the time coordinate. And you want to do any operation, so basically you've got, imagine, frame 1, frame 2, frame 3, 4, etc., it just goes on through time. Anyway, so what the B is doing when it's what they hypothesize and basically predict from the algorithm that they were able to replicate is what's going on is kind of an adaptive process of what's known as temporal and spatial integration. So spatial integration refers to the shutter speed. Temporal integration refers to the shutter speed of and the exposure setting. And spatial integration could, in kind of simplistic terms that I used earlier, refer to the sensitivity of the detector. More precisely, what spatial integration literally means is taking a group of pixels and just averaging over them through space, and then temporally you're taking a group of pixels through time and averaging over them that way, right? And depending on the strategy you choose, you're losing out one type of information. When you average through time, you're losing information about movement. When you average through space, you're losing information about size and generally about details. Now, ideally, when you're trying to talk about flight paths, the temporal information is probably a little bit more important than spatial information. That said, depending on the speed at which you're going through, at low speeds, you can afford to sacrifice temporal information at low speeds. And for low amounts of detail, you can afford to sacrifice spatial information. So what this algorithm does is it takes the stack of frames, for instance, takes 4 frames, and treats them as like one cube of information, and it looks for each pixel in that cube. It goes through and looks at what each of its neighbors are doing at any point in time or space. So if there's a lot of change through space, it will average over time, and vice versa. If there's a lot of change, if there's a lot of change in the intensity of the pixels that are its neighbors in time, so itself at different times, it will then average over space. And so what you end up doing is being able to take like an image like this, or rather, this you have to do this with video, of course, if you don't have time information on still. So you can take a single frame of the video and turn it into something that's actually useful for potentially driving your car at night time, which is what everyone wants to be able to do on my Toyota Gate and taking a whole bunch of money. So yeah, but that's software. Like software is cool and everything, but I mean, what's even cooler is if you, like, I mean, software. There's a limit to what you can do with software. This is able to run on a standard computer, graphics processor unit, multiple in parallel at real time for a small, I think it's 256 pixels by 256 pixels. Like that's okay resolution, but nothing. Like, you wouldn't get too excited by that. That's right. This thing is really cool. This is a fundamental shift in camera technologies. Whereas that other thing that I told you about is basically a standard camera takes a single frame at a time and exposes it and creates an array of bitmap output, right? This is a redesigned camera detector that basically operates like a retina. In the sense that rather than having just an array of photodiodes, what these guys over at Unilabs have developed is a camera that basically mimics the first 2 or 3 layers of a retina, in that each of the pixels in this detector array are hardwired to each of its neighbor pixels in such a way that you have like some center pixel, and then you've got like an array of something like this, where you've got 8 pixels surrounding the center pixel, and these are all hardwired together, so they're all talking to each other simultaneously, and they're all exposing continuously. And then there's some some algorithm that's being implemented in this system that basically works in such a way that if this center pixel is either twice as bright or twice as dim as the average of all of these pixels, then this center pixel will fire an on event or an off event. So it'll either send a 1 or a 0. Otherwise, well, actually, maybe not a 1 or a 0, because that doesn't make sense, because then it's got 3 states. It's got a neutral, and off. So it's probably like, yeah, it would be like a, sorry? Yeah, so that's like 2 bits, right? Anyway, so we've got a system where we've got on, off. So basically, just like a retina, we've got the on states and the off states. And so what this thing is actually doing is rather than actually, recording the luminance intensity of an image, what we're doing here is basically saying if there's a change in contrast at a particular point in this one pixel, and then you multiply that by the 120. This is an array of 128 by 128 of these things. So again, as far as resolution, like this isn't anything to get excited by if you're a resolution junkie. But if you can look past resolution for a second and like consider the applications of this sort of thing, it kind of starts becoming exciting, because what this thing is doing is it's continuously exposing and recording events of changes in contrast. Right? There's a huge. I need to show you a video because the output of this thing is amazing. Basically, what it does. If I go to my sidebar and I go over to YouTube and I show you what, this is just a quick demo of what the output of this thing looks like. And you may or may not be super excited, and I may or may not be able to show you because by the looks of it, Flash isn't working. Let me show you. There we go. All right, so this is Tony Delbrick and Toby Delbrick, and he's being recorded by his DBS sensor. And I don't know if you basically all the grey space in this image, there's literally nothing going on there. There is no information content. So for those of you who are familiar with image processing, that grey space needs to happen to it, right? The black and white dots are the leading and trailing edges of the contrast gradients, and that's all this thing is able to pick up contrast gradients. So when the paper starts moving really slowly, it stops responding because all it can see are changes, right? And so when you slow down the speed at which this thing moves, like the rate at which it changes, like just go. It's it's going on a place. No, play them all. They're cool. Anyway, so that's yeah. So yeah, this is like an example of overlaying the output of this camera with the output of a ordinary camera that you are actually familiar with, and then actually just putting it in the real time. We call it that one for the one events to be red and green. And yeah, so just actually. Yeah, this one's crap. Anyway, go back. Sorry. We go to Uber episode. That's not the one. Yeah, I don't think, does it? Anyway, yeah, this is basically a reverse engineered retina, and essentially because it's not functioning in a way like a camera, the output that it generates is super sparse. So there's a 1 hour, or rather, sorry, you can record an animal sleeping like overnight and end up at 128 or 128 and end up with a file that's literally a couple of megs, right? And then you can and basically, this is neat because they're the spike events on the YouTube video. Basically, yeah, it's because it's like hitting the spike event. What people tend to do in neuroscience is they take a train of spikes and they plug it into a speaker. So because that's a nicer way of understanding. It's easier to recognize a pattern of spikes when you hear it than it is to just look at it. So that's kind of a conventional thing. What was it saying? Right. So retina, super sparse. Oh yeah, because it's super sparse, it's really, really incredibly useful for doing anything to do with robotics, right? Like this thing, you can hook one of these up to a standard laptop to run in real time, like a robo goalie, which I won't go show you the video now. I totally recommend that you should look up the video of robo goalie. And it's basically like this thing. They use the visual input of this thing, and it's just a paddle that moves from side to side. And it's able to detect where the paddle is because essentially the way the robot works is by default it swings its arm, and it swings its arm in front of the camera. And then whenever it moves its arm, it creates a pattern, a leading and a trailing pattern on the detector, and so they can use that leading and trailing pattern to get an idea of where the robot's arm is in visual space, and they can use where the robot's arm is in visual space to calibrate the actual motors that drive the arm for the robot. And then you can do this where you can then throw objects at robot, right? And because the only moving, if you do it in such a way that the only moving thing will be the robot's arm, which it knows where it is, and so it chooses to ignore it. And then the only other moving object is the thing that was throwing it remotely. In almost like close to real time, the robot will be able to swipe across and just block any input. And it's like really cool thing to be able to do that. Like the other things that this thing is able to do is because it's only paying attention to movement, or yeah, because it's only paying attention to moving objects. It's like you can use it to track things really easy. Like some dude in Tokyo hooked this thing up to a device that just moves around like this, and you can balance a pencil on top of it, and provided that the camera is pointed at the pencil, right, the thing is able to balance the pencil. But that's provided the only thing that the robot can see is its arms and the pencil, and as soon as someone comes along and like puts a pencil behind it, then it completely ruins the whole thing, because then all of a sudden it's got like incoherent input. Yeah. I kind of feel like a salesperson because I really this is me trying to argue myself into not buying one, but rather I really want to buy one to make some robots, because like I mean it's fucking awesome. Relatively speaking. But yeah, so that's kind of two things that you can do with brains, or rather by knowing what a brain can do. That's one, two things you can make an algorithm, you can make a retina. And yeah, kind of where I'm excited is what's going to happen next, and that is, you got like, we're having this discussion earlier. This is like what, 1982. This is like this is like the third or fourth iteration of the Intel processor. Actually, this is more like the 10th iteration of the processor, or whatever. It's like, I think it's anyway. Point is, the actual iteration doesn't matter. The point is, this thing is a glorified calculator, right? And to some extent, yeah, so is this thing. But this is a glorified calculator that takes a stream of input, like a single stream of inputs, and produces a single stream of outputs. Whereas this is a glorified calculator. Well, maybe a glorified calculator. I'm probably leaning towards that probably is a glorified calculator, but it takes a massively parallel stream of inputs. And not just one or two, but like thousands of parallel streams of inputs, right? And does massively parallel computations on that input, and it produces another massively parallel complex output in the form of behavior and language and reasoning, right? And kind of the next slide is this baby, which is one of these chips, which is a integrated. It's a silicon neuron chip. It's an integrated array of basically model neurons, which this one was developed over at MIT. But basically, what we've got a very good working model of exactly what a neuron is, electrically speaking, and actually. In almost every level, we've got a very good idea of what a neuron is. I think there probably isn't one at which it's not well understood. But electrically speaking, it's basically just a cable which has some threshold that when it reaches that threshold produces some output, right? And I mean, electrically speaking, it's not too hard to model. You've got a couple of filters, and then like an if condition when those filters like. Once the threshold is reached, there's an if condition that produces some stream of output. And the cool thing is though that one of like a single neuron to do a single computation, right? In the best case, where we've got a small neuron, rather a large neuron, which is like what's known as a low input resistance, which means it's just going to act really quickly. Like best case scenario, in a typical neuron, they operate in the orders of 5 milliseconds or something. You insert a current into a standard neuron, and it takes at least 5 milliseconds for something interesting to happen, right? when we start talking about, and that's because of the way that these things work. Like, I mean, at the end of the day, once you peel back all the layers, this is a thing that shuttles around ions, which are big, and there's a lot of them, right? Whereas something like this, it shuttles around electrons, which are small and move really quickly, right? So a single logical operation on something like this is something that's happening in the order of a couple of nanoseconds. Like a standard transistor, like you take an input and produce an output, and do its operation in 3 or 4 nanoseconds, right? Which is 1,000 times faster than the simplest possible operation that you could do. That's 1,000 times faster than the simplest response from the simplest neuron that you can imagine, right? In practice, what that translates, like that 5 millisecond figure that I quoted to, that's only something interesting happening at the cell body. Like if you actually imagine like what a neuron looks like, I mean, it's got its cell body, and then it's got all these projections that go off into infinity, right? And then it's got like this massive output, right? And so if it takes something like 5 milliseconds for anything interesting to happen in this region, then you've got to add all the time it takes for that interesting thing to propagate down that way, and to propagate down that way, and so any sort of computation starts looking in the order of a couple of 100 milliseconds, which is really slow. And so, yeah, it's kind of why the integrated neural arrays are super exciting, because if you can imagine, right, like even if you do only model like something like a dragonfly array with something like this, which has a couple of thousand neurons in it already, right? It's not super complicated, but I mean dragonflies are able to fly around pretty well and not crash into things most of the time. So I mean it may not be a reasoning machine per se, but it's certainly going to be a lot more intelligent than calculator. Which, yeah, I think I'll leave that. That's kind of where I want to go with in my career. It's down that path. And this is Sonny. he's from American Robotics, or American Robots and Mechanical Man, and he thinks. Yeah.
So now we usually just do questions if anyone has them, and given that was complicated and cool, probably will be.
Yeah.
That's how they actually calculate reaction times to different events. We can calculate the amount of time it takes to travel between all neurons, and that can be able to actually, once you hear the reaction, your body to do something.
Yeah. Yeah. And actually, the reason that we can actually do that is because we can use electronics to measure that, which happens in an order faster than. The cool thing is, like, if you imagine, right, like, so like if you had, let's say it takes me, I don't know how long it takes me to count, right? Like we know that a computer can count almost instantaneously, right? And let's say it takes me like an actual tangible amount of time to count. Now let's say that we can use this system to model a simple nervous system, right? And to model like a simple reasoning process, right? In principle, like if we could model language with one of these things, and actually have two of them modeling language, like potentially we could have like a conversation that would take a couple of humans, like a couple of hours. We could see that in like a second or two. Like
That's interesting.
Yeah. And then yeah. So if you could, that's assuming that you can get it intelligent enough to make language. But I mean,
so if we can make it use like far in the future with that type of business systems, would they experience time at a lot faster rates than we do?
well, I think almost certainly yes.
Subjective experience of time is absolutely based on what's going on. That's why when things are happening around you at different speeds, it seems like the day is taking forever or taking no time at all.
Your value for the argument that we're going to single brain life into the model?
Well, I mean, I think that's the application that these things are going for now, simply because I don't think, well, they're going for that at the moment because this is research that's driven by neuroscientists, and unfortunately neuroscientists are interested in what's going on in the brain. And so basically these sort of things at the moment are being used to simulate simple nervous system circuits so we can understand better how nervous systems in real animals operate. That said, ultimately, if we were talking about this earlier, like a brain is basically a thing that stores memories and then retrieves them really quickly. And, like, if you could imagine, like, you have a system like that and recognizes patterns in those memories, right? So if you have like a system like this, like if you upscale it, not Sunny, but if you have a system like the integration array, if you upscale that so that it can handle, say, the sort of data sets that Google or Facebook goes through, right? Then there's no reason why you can't just plug in a massive data set to it and then see what pops out. Because the chances are what pops out is going to be some pattern in that data, and maybe it's a pattern that you've already accessed through some other traditional computational method. Maybe it's not.
And given that human brains are designed to pick up a pattern in 2 or 3 instances of similar situations, that's incredibly powerful for something.
Well, yeah, I mean, you consider the speeds again for a second. Like, I mean, I don't know how long it takes us to recognize a pattern. Like in a simple list, it's almost instantaneous. But there is some time cost associated, which is why people don't look at really big data sets and go, aha, I know exactly that all of these things are transcription factors or something like that. But there's no reason why something that's operating 1,000 times faster than us can do it 1,000 times faster. Or, 1,000 times larger, or whatever.
What about for real-time embedded systems instead of looking at a centralized brain like we did made up of chips which are emulating neurons, rather a system of smaller drones which are built up of simpler neuronic brains? So instead of building a human brain, you build a swarm of dragonflies in order to survey an area, for instance. How long do you see? How long do you think it'll be before practical applications exhibit themselves in that closer field?
Well, I don't know. This is where, like, as I said at the start, like, I'm more of a biologist, and so to actually tell you how long it takes for the technology to actually change is, I don't know. What I do know is, like, these chips already exist, and the field of robotics is fairly lively. So, and hazard a guess that something like a really simple drone application, that sort of thing isn't going to be too far away. I mean, already with just that artificial retina, like we already have that's been around for 3 or 4 years now. And there's applications for really simple, albeit trivial robots. But I mean, all you need to do is change what's on the end of the arm, and like a trivial application goes from being a fun application to something that's actually industrially useful, or maybe even militarily useful. I mean, yeah, like, I don't see it being itching. I don't imagine it being more than a couple of years, like, not even a decade, or something like that.
Any more questions?
So I was estimated at 790 do you think that these sort of creatures will be able to have self-consciousness?
Well, we don't really know what is consciousness.
I mean, so self-awareness.
Yeah, well, I don't know. I mean, I don't even know if it's really, is that a thing that's really, this is away from my area of expertise, but I'm throwing this to someone who knows a little bit more about psychology. Is self-awareness a thing that is...
It's not defined.
Yeah, so...
It's this giant great technical gap.
I remember reading about some AIs that can recognize one another. So that would be very similar to what the others do is have to be able to recognize themselves.
Yeah. I don't know, like, and there's, I don't know,
Isn't that what you put next to that?
yeah,
Where it can be exercised.
but that doesn't necessarily, like, to say that it recognizes itself, that doesn't necessarily mean what you and I might think it means, because when if I hear something like that, all that means to me is someone has gone to the trouble of incorporating an image of this robot into its memory and some if statement, if you see something resembling this, you know, update variable self-awareness or something. I mean, that sort of thing is kind of trivial to simulate. And I mean, whenever you start talking about robots that appear to have emotion or whatever, like, these things aren't they're just trivial simulations. Like, has anyone seen Nowbot? Which is another thing that I'm considering buying if anyone would give me like $16,000. But Nowbot it's marketed as like it's consumer electronics for super rich people. But it's basically like this little like 1 foot tall plastic dude that you know laughs and sings and dances and does all these like cool things like that seem and if you topple Nowbot over, it will cry. You know, and it's
Angus, stop thinking about hooking it up to an Iron Maiden.
Just the concept of buying a $16,000 robot to push it over to cry.
No, but the best one is though when people like because when people
Move over, servant.
when people do like the tech demos of now, they're getting him to do like his like one of his dance routines, and the dance routines are actually like remarkably complex, and so inevitably at a tech demo, he's going to fall over doing a series of complex movements. And so it's always hilarious. Like, you know, he'll be in the middle of like some ballet routine, and then like someone will trip over his cord or something, and just like.
But yeah, on that topic of sentience and that, if what you're talking about is what we would call a lived experience and an experience of existence, no, that's not well defined at all. It's been a shit of a thing to try to define right since Descartes. No one knows what the fuck is going on with this experience of being alive.
Well, but actually, I don't know. Is anyone familiar with the Chinese room thought experiment? Well, I mean, I'll just quickly run through it. It's a fairly simple one. Basically, the idea is there is some person who doesn't speak Chinese inside a room, and under the door, and inside this room is a book with instructions, and the instructions basically are, unbeknownst to this person, basically all the syntactical rules of the Chinese language. And what happens is someone will slip under the door a series of characters, and this person takes the characters and they'll go through the book and, you know, okay, I've got this character, I'll go to the book, I'll do, you know, this thing, and basically ends up in Chinese having a conversation with someone just by following the rules that are in this book. And then the argument is, well, does that person understand Chinese? And it's kind of the same sort of argument with consciousness. Like, here we've got a robot that, to all intents and purposes, appears to be having a conversation with us, and appears to be emoting, and appears to be doing all the things that I would say give the semblance of consciousness. Is it conscious? I mean, well, I don't know.
Is that the point where you make its brain out journey?
That's actually Descartes' argument, is that you can never know that another thing is conscious. You can only know that you are conscious, and that other humans appear to be conscious. The logical follow-on from this is that if you treat other humans' consciousness as an illusion, you're probably going to wind up in jail, so you should probably just assume that they're conscious.
I mean, that's two slightly different points. So the Descartes model is accessing being able to determine who is. It's an important question of whether you can work out whether someone's conscious. And then there's the question of whether it counts as consciousness. So in terms of that description, and whether there's a general difference between the sort of what you can identify in yourself as consciousness, and whether, say, like in an animal or a whether that is consciousness is, and then you sort of see whether there's something else that's going on, which kind of looks very like consciousness, but is it?
I reckon if it were able to build a system that takes multiple inputs and is like massively interconnected and, you know, to all intents and purposes, is basically a brain, then I reckon just as a matter of course, you will end up with something that resembles consciousness, if not is actually conscious. Right? But at which point, if you have done that, the question of is it really conscious becomes an uninteresting question.
What does it help you predict?
No, it doesn't help you predict anything, but it changes the ethical status. So, if it is really conscious, then keeping it locked in a room, making it do what we want, assuming we could, would be, to a lot of people, morally equivalent to slavery.
But what
Then
if
it unionizes.
But what if? Okay,
I'm not giving an AI to Bill Shorten.
But I mean, hold on. Just before you say that, why? Okay, this is not an argument I would, in my right mind, ever make outside of the concept of robotics. But why is slavery wrong?
Yeah, that's where you get into this basic idea that life is special, that there is something about life that is inherently good, and from that follow a whole lot of things about a fulfilling life and control of your own life.
Okay, so what does it mean to have a fulfilling life then?
Yeah, this is not. This is also.
Yeah, but ultimately, what I'm trying to lead you to is, what if I just program my robot to actually not give a damn about freedom and actually enjoy cleaning up after me? I mean,
Well,
does it
that's
matter?
like programming your child to make
Yeah, that's.
Well, no, I mean, I wouldn't make that argument with a child, but for a machine,
Well, that's the
why
thing.
can't I?
If it's genuinely conscious and therefore arguably alive, then it becomes very difficult to argue that there is something inherently different about a machine with consciousness and a child.
But
And
hold on.
therefore, if you could program a machine to do that,
But I
if you
can
work hard enough, you can certainly program a child to do the same thing.
But with my machine, I can actually determine what variables in the real world will make that robot satisfied and happy and feel like it's leading a fulfilled life. I can't do that with a human and wouldn't want to, but I can do that with a
Well,
machine.
that's the thing, is that comment you wouldn't want to.
No, but you couldn't make a child. You can't make a machine.
Well, that's
How do you know?
Simulator belief.
Yeah,
Simulator
well,
belief, yeah.
Simulator belief.
They would not have a real brain.
And if you argue that it has achieved genuine consciousness, so it has an experience of existence that is the same as what we've got, then in theory it's just a human where the neurons are made of silicon rather than whatever the hell proteins.
Let's say that it's not like a human because
Just a question.
That's a really good
Why do I need to give a damn about consciousness anyway? Why is my morally deciding factor whether it's conscious or not?
suffering.
yeah, but I mean, suffering comes down to a change in the state in what's known as like essentially the limbic system of the brain, right?
Yeah.
If we just choose not to include that part of the brain in our silicon brain, then there's no capacity for suffering. Ergo, no reason why I should give a damn about. Well, I mean, it's probably costing a lot of money to make, but otherwise, no reason why I should give a damn about the actual
Quite
life
possibly.
experience of my robot.
Quite possibly. However, one of the things that is still absolutely true of philosophy is that humans are irrational. If you say that suffering is the criterion and without a limbic system it doesn't suffer, therefore it's not a moral subject, sure, that may be a reasonable argument, and people may well still say life is different. For example, if you take utilitarian arguments about vegetarianism, there's an argument to be made that if a chicken lives a really ideal life, there's nothing wrong, and it doesn't suffer as it dies, there's nothing wrong with killing it and eating it, provided it doesn't suffer as it dies. On the other hand, there are people who will say, no, you are ending a life, and life is somehow innately special.
So, just on that topic of human being like ultimately irrational, just want to live with Peter Singer.
Yeah.
Peter Singer is like this. He's an ethicist, and he writes really interesting things. And a while back, like last year, 2 years ago, I read an article that I totally agreed with, in which he argues for. Well, actually, yeah, the argument was an argument for. No, it wasn't bestiality. It was for infanticide, actually. But it was a totally rational argument as to why there are cases in which infanticide is actually a rational choice, and
Killing babies. Is that the
No, but,
article
like,
where he writes?
thing is, like, the argument basically boils down to exactly the argument that I just expressed for robots, in that it doesn't have a limbic system, therefore no capacity to suffer, therefore it isn't a moral issue.
But is that the article where he talks about if the child will grow up and have no quality of life, then it's alright to end it?
Yeah, basically.
Yeah, okay, got it. I read that one.
Yes, a number of people have come down on both sides of that. There are people who say, no, it's alive, therefore you can't touch it. Assorted versions of that draw more or less flack depending on how it's applied to abortion. Where there are other people who say, actually, if you've basically got a head in a jar, it cannot experience, it cannot have meaningful existence, however you define that, then how can it have a life that's actually worth living? And that's a really interesting concept that's not at all well defined, and that as a society we seem remarkably reluctant to have conversations about what constitutes a meaningful existence, partly because it's political suicide from what I'm saying. No matter what you do, you will piss off a lot of people if you just go into that. And partly because it makes a lot of people really, really uncomfortable to start putting thresholds on what does and does not count as a worthwhile existence. Because invariably someone falls on the wrong side of that divide.
Well, I mean, that's a question of governance. Which is another question of governance.
Comes into much the same area though, in terms of how do we decide what grounds we will use to decide what's a reasonable thing to do. Because you're right, you could make a robot that genuinely loves to be a domestic slave, basically. And it understands the idea of freedom, it has evaluated the idea of freedom, but its enjoyment evaluation processes say, no thanks, I'd actually rather continue what I'm doing, freedom is an irrelevant concept to me.
Ah, so best breeds.
Basically. Basically.
So really they're robots.
I'm not sure I should still be recording this.
You really shouldn't. But at the same time, and you could even make a decent argument that is, assuming you could do it to a sufficiently high degree, equivalent to training a child to genuinely love cleaning up after you. And I'm aware that at a practical level it's really, really hard to bring that degree of brainwashing. But assuming you could make an argument that the two of them are morally equivalent. And there will be people who say, therefore we should do this to children. There will be people who say, therefore we should not do this to robots. It's really, really hard to say which side this falls under, because for most of our existence, we've not had tiny little programmable robots who wouldn't fight back if we tried to brainwash them. They're bite.